Hello, my name is Madeline Weller, and this is my Lab 2 projectile motion for Georgia Tech Physics 2211. Introduction for our lab, purpose and fundamental principles. So my lab layout was, or the purpose of the lab was to create a video of an object moving with projectile motion. To do this, I tossed a bouncy ball in the air next to a tape measure. I inputted the video into Tracker, which I used to find the position versus time graph and graph the experimental velocity and trajectory of the object. For my models, I coded the data from Tracker into GlowScript to find the drag and force due to gravity, and then I compared the data using a spreadsheet and Newton's second law. So here's a screenshot of my uploaded video that's in Tracker. My initial position that I found using Tracker was 0.00465 in the x direction, and 0.363 in the y direction in meters. As you can see, the ball is moving in the positive x direction the entire time, and then it begins by moving in the positive y direction, then the negative y direction after its highest point. My system is the ball, and the surroundings are the floor. I use the coordinate plane feature and the calibration stick feature in Tracker to align my coordinate plane to where the x position of the ball begins, and then I use the calibration stick to measure the tape measure on the floor and convert that to meters. In each frame, I track the point mass to determine the velocity of the ball. So here are the main physics ideas that we used and my reasoning equations for them. The first one is Newton's second law. So I use this in the form of the momentum principle, which is delta P is equal to F net delta T. And then I also use the velocity update and position update formulas for the GlowScript code. In addition to these, in this lab, we were required to use the drag force and calculate this, which moves in the opposite direction to motion, which is calculated as the force of drag is equal to negative b, which is a constant, times the velocity squared in the v hat direction. The acceleration of the ball is directly proportional to the force acting on the ball and inversely proportional to the mass. These are the Newton's second law principles that I use when calculating b and the other values in my lab. To find the drag force constant, which is b, I use the velocity at a given point on Tracker with the equation ma is equal to mg minus bv squared. These were the initial conditions set up in my GlowScript code. You can see that these are the first points on the Tracker data that I used. So my position was at 0.363, and I omitted the x value because it was too small to be significant. And then I put the initial velocity in there as well. Delta t was found by using the frames right here, the frame rate dt. And then I calculated b by the equation that I said previously, using the velocity of y, gravity, and ma to be 0. Here's my running GlowScript code for my calculations. And then these are the graphs. So this is position y versus time, and this is velocity y versus time. This is what my trajectory looked like in the model. And then this is position x versus time and position y versus time. This one got a little funky in the velocity, and I'm not sure why. It could be due to the change in trajectory of the ball. And then this is where I use the force of gravity equation, which would be negative mg in the y direction. And then the force of the drag, which would be negative b times the magnitude of the velocity squared times just the normal velocity. We also see that F net is the force of gravity plus force of drag, because drag acts in the opposite direction as gravity. And then these are the position and velocity update formulas to calculate our new velocity and new position. Data versus model results and error. My experimental data looks slightly different than the expected, but they are the same general shape. My experimental slope is steeper at the beginning and the end, and the expected is more gradual, as we see here. Here and then here. Possible errors could be as the object was moving through the air, the drag changes the trajectory angle at which is not accounted for in this model, where it's not directly vertical opposing gravity. Additional questions: what does it mean? Since the terminal velocity occurs when a falling object experiences zero net force, it will take longer for a falling object to reach terminal velocity than in my experiment. To do this, I could drop a ball from a very tall building, which would give it time to reach terminal velocity before hitting the ground. You can then use a plot to determine when the velocity levels off to constant. And then for the what if question, if the object were initially thrown straight up at the same speed as my experiment, it would be more time until the object hits the ground because it is traveling a farther distance instead of just out and down, it would be up and down.